Hello everyone and welcome. This is the final project of the Introduction to Simulation and Modeling course. I am Alfonso Cajiao and my group partners are Felipe Medio Real, Andrea Morales, Alejandra Peña, and Andres Romero. This project is about computational flow dynamics applied to agitation and mixing. The first part is about the behavior of a common Russian turbine impeller. The second part consisted of designing our own impeller geometry and analyzing its behavior, and finally comparing the two impellers. Agitation is a means whereby mixing of phases can be accomplished and by which mass and heat transfer can be enhanced between phases or with external surfaces. It is concerned with all combinations of fluids, gases with gases, gases into liquids, dispersion, liquids with liquids, dispersion or emulsification, liquids with granular solids, suspensions, and so on. The mixing process depends on tank or vessel dimensions, user baffles or draft tubes, and the bottom geometry. The impeller type, size, and the vertical and horizontal location also affects the agitation and mixing. And finally, the impeller speed. So why are impellers used? They are a rotating component used to increase the pressure and flow of electricity. There are many types of impellers and manufacturers use them for many purposes, depending on the desired outcomes of mixing. Choosing the impeller type could depend on the scale of the process, the fluid type, the phases involved, and the available power. This is the basic stir tank. Has 4 baffles to prevent the formation of a vortex and to prevent dead zone. Alright, so this is the nomenclature I'll be using along the presentation. To understand fluid dynamics and the phenomena involved in mixing, it is important to understand these main properties: the power number, and the shear rate. The shear rate is the property of interest, as the main objective of the project was to design an impeller with a higher shear rate than the Russian turbine. Impeller speed. Different impeller speeds were studied to understand the mixing at laminar, transient, and turbulent flow. Speeds were calculated using the Reynolds number, standardized to rotational speed. These are the speeds used. So impeller and vessel design. The vessel used for the analysis was small, probably a vessel you would use for research purposes, but anyway there are many ways to scale up agitation and mixing. This is the common Russian impeller. It has 6 vanes perpendicular to a rotating plate. The dimensions could vary, but you get the main idea. The impeller has been around for many years now, but it is still the impeller with the higher shear rate. Until now, let's see. The designed impeller had these dimension restrictions, so the geometry designed was similar to the Russian turbine, but varying some components, like the vane geometry and inclination. Despite the many studies reported, impeller design is still a very empirical process, so we had to be creative. As the vane geometry had more edges, higher shear force is expected. Simulations were carried out in STAR CCM+, a computational flow dynamics software. The setup consists of specifying the fluid volume, building a mesh, establishing the physical models, and refining some simulation criteria. The fluid volume was obtained by extracting the impeller from the vessel. This is the mesh setup. It consisted of polyhedral cells, which are shown to be better, with local refinements at the impeller. An automated mesh was created and it was configured to have a bit more than 400,000 cells. In this picture, the mesh seems to be fine, as the cells look homogeneous enough and there are not too much non-conformity cells, which are the cells that are not up to minimum standards. These are the physical models used. Rigid body motion describes how the impeller rotates and affects the fluid around. It is an unsteady study because agitation is a time-dependent process. It changes with time. At first, the fluid is static and then it starts moving around Despite some of the simulations are in laminar flow, the turbulent model provides a much more accurate description of the fluid behavior. And the kappa-omega turbulence model is a two-differential equations model that allows us to analyze the convection and diffusion generated by the turbulent energy. Also, we use the chill layer, and as the time is an important factor, the time step must be set up, and a maximum iterations per step, a maximum number of steps, and a total simulation time. This is the configuration we used. After the simulations were carried out, calculating the torque, the number of the Reynolds number, and the velocity and the rotational speed, the following curve could be obtained. This is the power curve of the impellers. And over here we compare the theoretical Rushton value, the simulated Rushton, and our designed impeller. It can be seen that after the transient flow, the values are very similar, as well as the behavior. Using the MATLAB CF tool, this model could be obtained. This is the theoretical curve for many impeller types, and the behavior shows that the simulated results are accurate. Despite the similarities, some errors can be found in these graphs, and this is the root mean square error, and this could explain why there are some differences. These are the velocity profiles of the simulations. It can be seen that around the impellers, the velocity is radial. This is because as the impeller rotates, it imparts momentum and energy to the fluid, and so the fluid moves, and this is what we see in the form of velocity. Over here we can see some circular behavior, and this is because of the friction of the walls, and because the impeller is sending the fluid actually upwards. Here in the Russian turbine, we can see the turbulent flow, and it can be seen that the velocity profile shows really very many chaotic parts, many chaotic behavior. It is not a predictable behavior as in the laminar.